Hello everyone, I hope you are doing well. In this video we are going to solve problem 1 from chapter 21 of Physics by Halliday, Resnick and Krane. This is volume number 2. Actually this image was shared by one of the students. It's a requested video, yes, and she wanted guidance related to these problems as she was confused about it. This problem is actually related to the Coulomb's law in vector form. The application of Coulomb's law in vector form. Vector form has to be considered while dealing with such situations, the situation in problem 1, because otherwise the answer would be different, and that's not something that we want. And we should be familiar with dealing the physical quantities in vector form and how to do the vector addition. So these things should be made familiar to us because we are at that stage of our life where we have to be familiar with tough situations as well. Once you have done enough practice, then it will become very easy for you to do this. Okay, so it's really easy, but it requires you to practice it enough times. Okay, now let's read the problem statement first, then we'll dive into the solution. The problem statement says figure 21.11, which is actually this figure. This figure shows 4 situations. As you can see, it's 1, 2, 3 and 4 different situations. Figure shows 4 situations in which 5 charged particles are evenly spaced along an axis. There are 5 charged particles in each case. You can see these dots are showing the charged particles and they are evenly spaced. Evenly spaced means that the distance between every 2 charged particles is same. Okay, and they're all equal. Like the distance between these 2 charged particles is d, the distance between these 2 is d, distance between these 2 is d, distance between these 2 is d as well. Okay, the charged particles has equal distance. Then we have second situation. We have these charged particles and the distance between them is d as well. Okay, the distance is always d between 2 consecutive charged particles. Consecutive means the nearest ones. This is the charged particle, the nearest to it is this one, so the distance between them is d, and so on. And distance between between this and this will be 2d. It's like this d and this d. The total of distance between these two will be 2d, and that is how we'll proceed. Shows 4 situations in which 5 charged particles are evenly spaced along an axis. The charge values are indicated except for the central particle, which has the same charge in all 4 situations. Here they are telling us that we have shown the charge on each of the particle except the central particle. Okay, we can see that all of the other charge bodies are calibrated. They are given a specific charge, and they are saying that we have now shown the charge on central particle, and that will not affect the solution as well. The thing that we are seeking, it will not be affected by it. And we have the similar charge. They all have similar charge. It means, let's say we'll let that it has charge q, so it's charge q in first situation, charge q in second situation, charge 3 in third situation, charge q in fourth situation as well. The charge will remain the same, but we don't know what actually it is. While in other cases you can see the charges are different in each of the situation, so that is why they mentioned it separately, especially. So what we have to do, we have this configuration. Now rank the situations according to the magnitude of the net electrostatic force on the central particle greatest first. So we have to rank all of these situations based on the magnitude of the net electric force on the central particle. What we have to do actually is to find out the net force on the central particle due to all these charges, neighbor charges. Okay, these are 4 charges. We have to find out net force on this central particle for first situation, similarly for second situation, similarly for third situation, similarly for fourth situation separately, and then we'll compare the results and we'll see which of the situation shows the greatest force on the central particle. Okay, and then we'll arrange them in descending order. the greatest first, then the next greatest, then the next greatest, and then the least. Okay, so that is how this problem will be solved. This no that is how that is what we need to do. Now let's solve the problem. I have also drawn it here, the same configuration, so that we can refer to it again and again. First of all, we'll find the net force for the first situation. Okay, now let's do it. Okay, so this is the situation number 1. Situation number 1, we'll solve for it first, and before doing that I have drawn it. Let the charge on central atom, okay, sorry, on the central charged object be q. Okay, so let the charge on the central object is q, and let the distance between any consecutive charges be d. Okay, consecutive, its spelling is this in clear writing. It's cu. Okay, so we have this situation now, so that the distance between any two of the charges is d. Okay, and now the expression for coulomb's force in vectors form is given by expression for coulomb force in vector form is given by in vector form we have F, which is coulomb force, is equals to coulomb force is actually the electrostatic force, so they both are equivalent terms. It's like q1 q2 k over r square r unit vector. Now let's put the value of r unit vector. We know that r unit vector is equals to r vector divided by the magnitude of r vector, which is r, similar to the one in the denominator. So let's put this right here. It's r square, it's r from here, and it's r vector divided by r cube that way, where r is the magnitude of this separation vector r. R is the separation vector which shows the separation between the central atom on which the force is intended to be calculated and the charge, the other charge, okay, whose force on this central atom is being studied. For example, if I'm considering this charge, then it's the second charge and this is the first charge, and so on. We'll see it later on. This is the formula that will follow. Okay, let this be equation number 1. Now let's make a vector figure in which we define a coordinate system so that it becomes easy for us. Now consider figure 2. This is figure number 1. Now let's make figure number 2 and we'll solve the rest of the question in reference to that figure. Now we are going to draw the figure 2, which will involve the detailed description of the case, and through this diagram we will be able to find the net force on the central atom for situation 1, and similar procedure will be repeated for the other situations. So the description for situation 1 could be longer, but for the rest of the cases it will become shorter, because we would be repeating that method, and in situation 1 we are learning it. Okay, that is why it might take a little bit longer, but once you understand the method it will become easy to do for situation 2, 3 and 4. Okay, so bear with me, have some patience, because teaching someone and making someone learn something in a better way requires time. So I request you people to have some patience and enjoy the process of learning. Here I have redrawn the diagram. Let's draw the coordinate system. This is I'm taking it as along x direction. Okay, so let the central atom on which the forces needs to be determined is at origin. Okay, let's say this is y-axis, nothing is on y-axis. Okay, I'm just making this line to make it clear that this is at origin. Okay, the point of intersection of two axis line is called as origin. So this is at origin. Okay, now we know that this distance is d. Okay, and the second distance is 2d. We are writing here the magnitude. We know that a vector, let's say r vector, which is the position vector, we have to find out it separately for each of the charged object placed at different positions with respect to the central atom. So we have to find it for all of them, but we need to have a general formula in our mind that r vector would be equals to the magnitude, which means the distance from the central atom, which is always a positive quantity. Okay, distance or magnitude is always positive, multiplied by the unit vector. Okay, here the unit vector will be corresponding to the x direction, which is I hat. Whether it will be positive I hat or negative I hat will be, we'll know it later on when we'll be dealing with the case. Okay, so this is the simpler formula that we'll follow. And similarly here, this object, charged object, is at a distance of d from origin, and this one is at a distance of 2d. Okay, they're all positive. Let's draw the vector r. Okay, r vector, since we are finding the force on the central charged object, the head of r vector will always be at this central atom, while the initial tail will be at the charged body which we are considering. Okay, let's consider this one first. I'm using green pen for this, and starting from initial point will be at the charged object, while the head will always be at this central body. And the position of vectors is arbitrary here. I have drawn it above the axis line to make sure that you are seeing it. Otherwise the force is along this axis line. Actually the force is along this axis line. Okay, but if I will draw it for this one, and if I'm going to draw the vector for this one, it will be merged and you will not actually see it, but actually the vector is here. Okay, I hope you got my point. Now what is the magnitude of this vector? Let's say this is r1 vector. What is the magnitude of this r1 vector? It's d. Very simple, that's the magnitude. Now we should know the unit vector, and we can see here this is pointing in negative x direction. This is negative x direction and this is positive x direction. Negative x means negative I hat. Since it's pointing in this direction, it is pointing in this direction, which is negative direction. That is why we are taking negative I hat. So this vector is given by minus d I hat. Okay, and its magnitude is d. That is really simple. So this is the first one. Now for second one, r2 vector. This is the similar case. R2 vector, starting point is this one and end point is this. So this is the vector, this is the starting point, end point will be the as I told earlier. So the central object, and the magnitude is 2d here. And what is the unit vector? It's negative I hat, negative because it's pointing in negative x direction, and unit vectors points the direction of a vector, and it's in negative direction, that is why negative I hat. So we got minus 2d I hat. Now let's consider these two, and for them I'm using different color, that's orange. And for this one, let's call it as atom number 3, object number 3. This is initial, and this here the head. Okay, the head of vector will always be at the central point, while initial the object under that we are considering, and this is the one, and this is the vector. And let's say it's r3, its magnitude is d. As I told earlier, magnitude is always positive, while direction could be positive or negative. So direction, now let's see what the direction of unit vector is. We can see here it's pointing in this direction, in positive x direction. This is positive x direction, this direction is positive x, so it's positive I hat and it's d I hat. What's r4? You can guess it right. It's 2d I hat, simply positive because it's pointing in positive direction, and these are the separation vectors. Okay, these are the separation vectors. Now let's write the expression for coulomb forces. The net force F net on the central atom will be equals to F1, force due to first this one, plus force due to this atom, plus force due to this atom. Oh, why I'm saying atom bar bar charged object. Okay, you got it what I'm saying. These are all vectors, and you know the formula that we'll use here. We just need to put the values q1 q2 by r cube r vector. We know r vector, we know r, which is the magnitude of r, and we know these values for all of the vectors. q1 will be the central atom's charge, which is q, and q2 will be the charge understudy, the other charge understudy. For example, for first it's this, for second it's this, for third it's this, for fourth is this. So let's put the values one by one. It's k, q1 which is q, q2 is plus e. Sign of charge will be taken into account as well. Okay, then we have r cube, r is d cube simply, and r vector which is minus d I hat in brackets because it's negative sign. Then plus we have k, q, then the charge on the second object which is minus e, so bracket minus e divided by here the magnitude of distance is 2d, so it's 2d with whole cube over it, as the formula depicts, formula number 1, and r vector which is minus 2d I hat. Then plus sign f3, k, q, it's negative e divided by the distance is positive d cube, and vector is d I hat. Then plus sign k, q, it's negative e again, and distance is 2d with whole cube over it, and 2d I had. Now let's simplify it, add it, and we'll get the net result for first situation. Here we can see that this d and one of these d will be cancelled out, so it's d square in the denominator which is left. Negative will come here, so it's minus k q e by d square. I had it's minus k q e by d square. I had. Then we can see here this negative and this negative sign cancels out and we are left with positive. Then 2d and it's 2d whole cube, so 2d, one of them will be cancelled out and we are left with 2d with whole square over it, which means taking square of this whole quantity, which gives 4d square. Okay, we'll write 4d squared later. So kqe over 4d square I had. Over 4d square I had. Then we can see here this d and one of d cancels out and we are left with minus kqe over d square I had. kqe over d square I had. And lastly we can see here it's positive and negative cancels. No, they do not cancel out, it's negative. Resultantly that we will get here negative, and one of the 2d cancels out and we are left with 2d with whole square in it, and we'll write 4d square in the denominator. kqe over 4d square with negative sign, so negative sign is all, I wrote it already. I had. Okay, we can see here that's the positive one and that's the negative one, equal but opposite in sign, they cancel out and we are left with they both are same and both are negative, so minus 2 k q e over d square I had. This is the net force on in first situation. Okay, this is the net force in first situation. Here the negative sign shows the direction of the force, like where the net force will be, and the magnitude of the net force is given by 2k qe over d square. Okay, this is the magnitude. The magnitude of net force is something that matters because we have to arrange the situations based on the highest magnitude of electrostatic force experienced by the central atom. This is the magnitude, and let's now do it for the second situation. Let me draw the second situation. Now it will become really easy for us since we now already know that how the things will gonna work, and you will see that we'll do this really earlier than the one before. This is the central atom. Okay, I always say atom, it's object. It has a charge. I have already drawn it. You can see here plus e plus e plus e, and the last one is e. It's negative e, it's plus e, it's plus e, it's plus e. You know, its position vector is like that, and this one's position vector is like that. Okay, 2d position is d, it's d, it's 2d, it's 2d, and it's d, and unit vectors are also evident. Oh, it's positive I had because in positive I direction I had. These are negative I hats, negative I hats. Okay, these position vector will remain the same for all the situations, but the charges are different only. Okay, so the r's you will get will remain the same. These are the same r's that we got for situation 1, but what becomes different is these charges. Okay, so that's really simple. Now let's find the net force that is equals to net force in second situation. Let's call it as Fn2. Let's call it as Fn1. That will be equals to force due to this it's k q, charge on its q, plus e, so it's plus e over d square, d cube, because the magnitude is d cube, and minus di hat, its unit, its vector is minus di hat. Then plus sign, k q, the charge is minus e, the vector is minus 2 di hat, okay, and the magnitude is 2d whole cube. Then plus sign, k q, the charge is plus e, that's good, vector is di hat and magnitude is d cube. Then plus sign, k q, positive charge, so it's again e, and the vector is 2 di hat, and the magnitude is 2d with whole cube over it. Now let's simplify it and let's see what's gonna happen. We can see here this one, it's kqe, this kqe, it's minus di hat, it's plus di hat, d cube in denominator, so they are equal but opposite in magnitude, so they will cancel out now and they will add up. You'll see that it's negative and negative will become positive, and it will become positive. This 2d and one of these cancel out, and it's 2d with whole square over it that's left behind. Here the same situation happens, so it's kqe I hat divided by 4d square, and this is the same thing, I hat over 4d square, and if we add them up it becomes 2, because it's same thing, so it becomes 2 times kqe I hat over 4d square, 2 ones are 2 and 2 twos are, so it's kqe over 2d square I hat. So the magnitude here is kqe over 2d square. Okay, it's 1 over 2 kqe over d square, and yes, so let's write it here. F2 and is for the second situation, it's 1 over 2, taking 1 over 2 common, okay, kqe over d square, a magnitude, okay, so it's that. And in first situation it was 2 times kqe over d square. You can see it's half of it and it's double of it, so yeah. Now let's see the third situation. Now you can see that how easily we are doing it, and I think I don't need to draw the diagram again and again, because we now know the vectors are same, okay, the right vectors are negative and the left vectors are positive, so simple is that. And now here it's negative e in this direction, positive e here. Let's see how the situation goes now. Okay, we should draw it. Negative e here, the central atom, positive e here and positive e here. This is the third situation. The vectors are already known, it's negative di hat, and this one is negative 2 di hat, it's positive di hat, and this is positive 2 di hat. Okay, now let's find the net force. It's force due to this one, it's k q, charge is positive, vector is negative di hat divided by d cube, plus kq, this charge is positive, plus e, the vector is minus 2 di hat divided by 2d with whole cube over it. Then plus sign, we have this one, kq, negative e, vector is di hat divided by d cube, plus kq minus e, okay, vector is 2 di hat over 2d whole cube. All right, and now let's see if something cancels out. No, I don't think so. Nothing cancels out here this time. 1d cancels out here as well, so it's negative k q e over d square I hat. I'll write this one next to it. It's negative again k q e over d square I hat. I'm writing this and this together because they are more similar. This 2d and one of these cancels out, the same thing that happened before. It's negative sign here, k q e I hat over 4d square, and here negative k q e I hat over 4d square. Let's add them up. It will become negative 2 k q e over d square I hat negative, these are same, so it becomes 2 times k q e over 4d square. If you are confused, you can take LCM. Now minus 2, this is 2 ones are 2 and 2 twos are 4, so 1 over 2 is left. Taking kqe, okay, let me write it again, then I will take common. Minus kqe I hat over 2d square. Now I am taking kqe over d square I hat common, so that we can simplify what's inside. Negative kqe over d square and I hat is taken as common, and we are left with 2 plus, since negative is taken common, that is why I am writing plus inside. 1 over 2, taking LCM, 2 plus 1 over 2. Let's find them in rough work. What is it? It's 2, 4 plus 1, it's 5 by 2. So we are left with minus 5 by 2 kqe over d square. Okay, I had, and what's the magnitude? The magnitude that we got is f3, and magnitude is equals to 5 by 2 kqe over d square. This is the third situation's magnitude. Now last situation, the fourth situation. Here is the fourth situation. You can see negative e plus e negative e. That's the fourth configuration. Let me draw it. Negative e, positive e, that's q, positive e, negative e. Okay, vectors are same. You must have memorized these vectors, and they will come in your dreams if you are watching at night. At least I'm making this video at night, and I'll see them, I'll see these vectors in my dream because that's something that happens to me whenever I'm doing a certain thing frequently. Net force in fourth situation, thank God. Force on this kq positive e, vector is minus di hat divided by d squared, oh sorry, cube, plus kq, it's negative e, vector is negative 2 di hat, okay, divided by 2d with whole cube on it, plus this one, it's kq positive e, and di hat is the vector, divided by d cube, plus kq, it's negative e, the vector is 2 di hat positive, and it's 2d whole cube. Okay, and here you can see this is kqe minus di hat by d cube, and this is plus kqe di hat over d cube. They cancel out. Similarly, it's negative and negative become positive, and this is whole negative, so it's positive, and this is whole negative, so they cancels out as well, and there is net force equal to 0. It has the least magnitude because the net forces cancel out. Now let's categorize. Now we got f1, and the first most was 2 into kqe over d square. Okay, f2, in second situation we had the net force 1 over 2 kqe over d square. Okay, in third situation we had 5 by 2 into kqe over d squared. and in fourth situation it's 0. Now let's see which maximum and which is minimum. 5 by 2, what is 5 by 2 equals to? Let's do it. Or 2 2s are 4, 1.0 to 5s are 10. It's 2.5. This is actually 2.5 times kQe over d square, and we can see here 2.5 is greater than 2. So this, in this case, in this configuration, the central atom experiences the maximum force. Okay, you can see here kQe over d square is common in all the situations, so the factor that is being multiplied to it will decide which force will be maximum. So 2.5 is the greatest factor, that is why in third situation the force will be maximum. So this is the greatest. The next greatest is 2, obviously. The third greatest is half. Half means less than 1. Okay, this is the third situation, and in fourth situation where the net force is actually 0, this is the fourth. So let us categorize the situation in terms of these symbols. Maybe F3n is greater than F1n is greater than F2n is greater than F4, and you can write it that way, or you can write this wording as well. Situation 3 is greater than situation 1 is greater than, situation 2 is greater than situation 4. So that's the answer. I hope you got it, and I'll meet you in next video. Till then, take care, goodbye, like, share and subscribe. Yeah.